This conference will now be recorded.
All right, welcome to the few people we have on the phone and those of you watching on the recording. Thanks for coming along to the ESIP and USGS Community for Data Integration IT&I Tech Dive webinars. This month we have Michael, is it Rilee? Rilee?
Correct.
Yeah, Michael Rilee presenting some work that he's doing on a NASA Access grant called Spatial Temporal Adaptive Resolution Encoding for Scalable Integrative Analysis. Was able to catch his talk at the last ESIP meeting. It was pretty cool, and this kind of goes together with the last month's presentation on discrete global grid systems. These two technologies seem to have a lot in common, and we are kind of digging into this space a little bit in this 2-month period. And yeah, thanks for doing this, Mike. And with that, I'll let you take it away. If you can do 20-30 minutes, we can have a little talk, and then we'll call it a day. So thanks a lot, and go ahead.
Very good. You're welcome, David. Yep. My name is Mike Rilee. I'm the PI for the STARE project, and some of my collaborators, co-PIs are over there, and we have some collaborators at NASA Goddard Space Flight Center, and also we're aiming to do some work with the folks down at NASA Langley as well. This month's talk on STARE really does have a nice dovetail with the previous talk by Matthew Peirce, who provided a lot of important background information, and it's really the same space that we're working in. There are some key differences and a difference in the perspective, and I hope by the end of the talk today you have a better appreciation for what some of the differences are. You take a quick look at this. This is a summary here for those of you who want to see a quick little abstract. I'm going to be talking about how we're looking at indexing geodata and doing it in a way that takes into account both spatial and temporal indexing. But most importantly, we're looking at a way to being able to scale this up to use parallel and distributed computing to take advantage of the volume of the data that we have. And also we have a problem with variety, and that's really one of the key things that we're going after. Some folks have said that our scheme seems to be somewhat complex, but I don't think that it's more complex than some of the other systems that are out there that involve similar recursive tessellations of the sphere. And in any event, very few users would actually need to get down into the weeds to actually use the system. And we expect to provide most of the functions through a high-level interface. We're even developing a Python binding for the thing as well. And with regard to the DGGS, it would be very interesting, and one of the action items that I'm going to take on is to line up to see how compliant the STARE approach is to the DGGS standard, and that'll probably help folks understand how to work between the two worlds. So, outline of the talk. A little bit about the problem, a little bit about our particular approach, and then pretty rapidly we'll get into the conclusion. So fundamentally, we have in earth science, we have lots of data, and in order to use that, in order to deal with that volume, we want to be able to make use of the massively parallel computer systems that we have in the cloud, and also some folks are setting up on their own. And the idea is that, well, what you want to do, you want to slice up the area of interest and then distribute each of those chunks onto the different resources to make the best use of the data and the computing resources. So it's a pretty standard parallelization technique. And if you make your chunks too large, then you're not going to use your systems so well. So for example, we have one big block over there which is devoted to North America, and that gets mapped, say, for example, to one of your computers, you're not making very good use of your massively parallel system. So instead, what you want to do, you want to go to smaller chunks. So North America shows up on that one guy in the back instead of showing up on all 8. So divide up into smaller chunks, and then you'll get a better discretization across your parallel resources, and you be able to better scale your volume. But there's a problem. We have diverse data. It's not just grids. You have swath, you have grid data, you have simulation grid data, and you have point. And the thing is that each of these guys are stored in arrays with their own native array indexes. And it would be great if we had an index that would be apply to each of these systems so that you'd have a universal way to get at the data in each of these different data types. And let's see. So for example, if we have a grid data, swath data, and point data, and you can see that I'm indexing the grid with the indices L and M. Swath is at an angle to that, and the swath, you notice each of those different field of views for the instrument has its own slightly different shape, being larger out towards the edge of the swath, and we're going to label it with I and J, different from L and M, and then the points, they show up wherever they happen to show up. And so this is what you want to do, is that you want to identify a particular region of interest and then bring all the data from those different kinds of data, different data sets into that one particular region of interest and compare it. So most approaches to indexing the data these days that depend upon the native array indices really make it difficult for an end user who has to go in, understand the semantics of each one of those native array indices, and then sort of cajole it around to something that they can compare with other data sets. And broadly, this comes under the categories of taking ungraded data and putting it onto a grid, and then regridding that data from different data sets so that you have everything on one grid to compare it with. That's a lot of work. It's a lot of effort. And what we're trying to do with STAIR is provide a single universal index that you can take these different positions and then identify them, run set logic on them, and bring them together using those parallel resources. And let's see, the way we get into this, well, we want to have something that covers both space and time. It needs to be uniform so that we can apply it to all different kinds of data sets. We want the STAIR efficiently collocates the data for parallelization so that we can work with small chunks. Small chunks have both locality in physical space, and they also have locality on the computational space as well. So usually when you're going to compare two pieces, two observations, that's the kind of locality which works best for you, because you have to have the locality in physical space in order to compare them. But in order to reduce the amount of communication between the different computers, which really slows things down and makes things more expensive, you want to be able to have those same geolocations located on the same computer locations. Now, like many others, we're working with a quad tree or cursive quad tree for the spatial component, because it puts a tree data structure onto the sphere and helps you efficiently find things. And we also can apply that to efficient set operations as well. Now, we have something similar set up for indexing in time. However, I'm going to put off talking about for the most part, since it's not as well developed part of the API, and it's easier to see and more interesting to take a look at what we're doing with the sphere. And also it's more directly connected to the DGGS. This is a little bit of the project programmatics that we're working with. We have a group at UCSB which is going to apply our efficient indexing scheme to some snow map calculations. And we're also working with James Gallagher of OpenDAT to actually plug a server-side function that uses stare, so that an end user may be talking to a OpenDAP client, making a request without appreciating the fact that on the back end we're using stare to parallelize the data access. Now, what is the stare spatial encoding? As with DGGS, it's very similar in the sense that we're using a recursive tessellation of the planet. Currently we're starting with a octahedron, which is projected onto the sphere, so that we have geodesics in between the nodal points. So all the edges in our system are actually geodesics, or great circles. And that's one of the main differences that we have between the stare spatial system and the equiaerial ones, where it's my understanding that in the equiaerial meshes, you have to get away from using the great circle edges. And we're using the great circle edges there in order to help speed our calculations. And that's something that is just a fundamental need for what we're doing in order to keep our lookups and our indexing as efficient as possible. So we have a quad tree hierarchy, and then what happens is that we have a particular way of dividing up and numbering the triangles as we go through the different levels of the recursion. And then the encoding actually keeps track of which triangles at each level we go through in order to get to a particular point on the sphere. So if you pick a point on the sphere, like this little red one over here, and then we keep track of, okay, we're on the top one over here, that's a 1, 0, and then we're in 1, 0, 3, and then so on, keeping track of which branch of the tree we're in as we go down to higher and higher resolutions. And for example, with our current configuration, we start with about 3 bits over here, and that tells you which octant you are on the root polygon. And then we have 27 levels of trees that we can use, and we just use this to map locations, to map these triangular regions onto a 64-bit word. Also, we have mixed into that 64-bit word a bunch of bits set up for keeping track of what level of the recursion that we're at, and we treat that as a resolution of the index. And so that's the way that we can actually keep some. Okay, let's see. Somebody's asking to be made presenter by Michael Ariad, but I'll just keep on going as long as everybody can hear me. And so what happens is that that resolution tells, we can link a particular observation with both its location data and a rough degree of what its physical size is as well. And so we have that both location and resolution information encoded into this 164-bit word, which is really interesting from a database and allocation, a computer allocation standpoint. So for example, here we have a comparison of our stare versus a floating point encoding. We have latitude, longitude, and then example up on top, and then we have the stare spatial ID for a 10-meter triangle. And you have 2 different ways of referring to the same point on the sphere. So this is a rather busy graph here, and we can go into it in more detail if folks wish to talk about. We have about 7-centimeter leaf triangles in the mesh, and this is talking at a very fine resolution level, but it just goes to show that set operations correspond to comparing the different IDs with each other, and then seeing how many of these bits, or seeing how many of these levels actually compare. And that's sort of what's happening there, is that you're actually comparing which part of the trees that you're in. Now, all of that is really down in the weeds. It's because what happens is that for the end user, all they need to know is that, oh, I have a particular region of interest that I'm interested in. It's covered by these triangles, which correspond to these numbers. And then all I have to do now is just compare these different numbers together. Let's see, I think I pressed the button. All right, so just to restate the idea that I was talking about over there, what we do is that we take the data sets and we chunk it up according to these stair triangles. We find an object or a region of interest that we're interested in. We can use that to subset or select out the related data for this phenomena that we're interested in. And because it's chunked up, all this is occurring in parallel on distributed computer systems, and then we can bring those different kinds of data together and then compare them. There again, at this last step over here, you are going to have another regridding step, but essentially everybody has to go through that at some point. This is about the first 5 levels of the stair indices, and the thicker lines you can actually see where the root octahedron is projected onto the surface. What I've done here is that I've colored up a bunch of chunks with different colors of gray. This would be scattered across a 16 processor computer. We could actually do more, but this gets the point across. And then finally, we've taken a single swath from, I forget, okay, here's a single swath data set, and you can see how it cuts across the different colors of gray. And so that, of course, that would tell you that you're actually being able to distribute this across your parallel resources, helping you to scale in volume, in addition to scaling in variety. One of the interesting things, though, is that once you have this indexing in place and you have the different data types registered with these indices instead of, for example, lat/lon, once you use these indices, you can actually do things like a very simple join. Now, in this particular setup over here, I was working with the SciDB array database, and what we had done is that we had taken some NMQ radar data on a grid, and then we had taken those grid points and indexed them with the stair spatial ID, and then laid it into an array. And then in another array, we did a trim swath and laid that in according to its stair IDs as well. And then with the database, we just did a simple join. And where the indices lined up, you magically brought these two gridded and swath data set together very quickly, and that's the actual command that we use. We didn't have to write any other special command after we had already indexed the data and loaded it according to its array indices. And this particular database was running on a 28 node computer, so we were able to join a week's worth of the NMQ and NMR and trim data in just a few minutes, less than a minute, on about a 28 node cluster, if I remember the actual number correctly. All right, so for a little bit of indexing trouble at the beginning, a little bit of investment in that, you can naturally pick up parallelism. In fact, we were working with some folks, I believe at the University of Nebraska, and they said, okay, we've taken some data, we've indexed it using the stair spatial ID, a couple of different data sets. Now, what do we have to do in order to parallelize it? And I said, well, you've already loaded it into your parallel array database. It's already parallelized. And that was the end of that discussion. So it's one of the very nice things that you get by being able to use your stair spatial index that way. Here's a little bit of an example of that join that I was talking about before. On the top, you have the NMQ gridded data. Down below, you have the trim data. And one thing to notice here is that we were also doing, not only were we doing the join in the spatial component, which is all these little triangles here, it's also being done in the temporal component as well. So you sort of have a 2-dimension plus 1 dimension here. And this big long number over here, that turns out to be the temporal ID that we were using. And so each one of these triangles has its own 64-bit word. Here's another 64-bit word. And we're actually looking at about, I think it was four different granules that were actually joined during this very large piece of analysis that we were doing. So that's something that just essentially falls out when you're using the stair indexing scheme. here's another example that's essentially the same one that we were talking about before, where to the right you have data from one time, to the left of the blue line you have data from another line, and then we're just comparing the two temporal IDs to make sure that the two data sets are lining up, and then we co-locate them in space as well. Okay, so these are all essentially going over the same thing. So we can just move along this. In this particular one, we make a point that we can actually do conditional subsetting, where we have a criteria set on one data set, for example, the NMQ data, where you have precipitation showing up in the radar, and then we selected data out of the trim data set simply by doing by collecting the set of stair indices that corresponded to where the NMQ satisfied the threshold, and then we can go over to trim and just pull that right back up. This is an example of dealing with the variety of data that we have in an integrated way. So sometimes we get a question about the coordinate systems that we're working with, and presently we're working with NASA Earth Science data, and so we're essentially using WGS 84 for that. The current status of the project, we're about a year into the Access project. We're developing a new simplified API so that the end user doesn't really have to go in and twiddle any bits at all. We've added the temporal indexing, which proved to be a bit more interesting than I would have liked to. So we've actually gone towards using some astronomical standards so that you can actually have an approach to time that is strong enough to be able to compare spacecraft and interrelates data from different spacecraft. We're developing a Python interface, and that's something that I'm personally excited in, because that'll draw in a lot of capability, and in particular visualization. That would be a great step forward. We're working on making some of this available on the server side with OpenDAT, so that folks can maintain their familiar approaches to working with the data, and then they'll be able to pick up the parallelization on the back end. And one of the things that we want to do is that we want to talk to others and work with others so that we can take important pieces of functionality and then add it to the API. Comparisons to DGGS. This particular picture here actually shows some of the spatiotemporal aspects of it. This is actually a moving object taken from the data associated with the Hurricane Irma forecast. What we have is that sort of in the vertical direction, going from orange up through blue. Those are different time slices, different forecasts for the Hurricane Irma, which went around a few years ago, I think. And we show a number of different of these objects and how they're situated in time, where you get the spatial stair ID, and then in time you also have the temporal ID as well. So you have Key West, which is shown in red over there. That one's not moving very much, and then we have sort of a generic model sensor trajectory moving around in an orbit about Key West, and then you have the hurricane itself moving through. And this is all described by just a handful of 64-bit words, which you can then put into your database and extract data, or use it to select data and integrate data from different systems. So it's a little bit different from the DGGS in that sense. We have a spatial temporal focus. We have an adaptive resolution, which is actually embedded in the encoding as well, so that you're not just talking about locations in our geolocation. You're talking about a particular region on the surface of the Earth. That puts us a little bit at odds with the DGGS approach, which prefers an equiareal approach. But that we have to make trade-offs in what we're trying to do. We have a focus on indexing and logic for selection and distribution across parallel parallel computing resources. And we are really focused on adapting our system to diverse data. So in some sense, the spatial ID and the temporal IDs, they adapt to the data and contain information about the data to help us perform that set logic. A couple of the trade-offs that came to mind when I was thinking about Matthew's speech last month and what we were doing over here. We don't really store the grids very much. We calculate a lot on the fly, which is one of the reasons why we're very interested in taking some pains to keep our calculations relatively efficient. With our focus on great circles and that sort of vector algebra. We have simplified computation for constructing different edges. There was some talk about the areas of the data and how you would use them in the mesh to actually do some analyses. And we're not really coming at this as a grid that you would be doing analysis on. That's another step in the workflows that we would support. Putting things on a grid and dealing with areas there. We can and do construct areas of the different regions that we have in our triangles, and that's possible. We can do, for example, area weighted means and things of that nature, but it's not really where we're coming at, and that's not a near-term goal for us. Going beyond STAIR, I've mentioned a few times that we're focused on being able to find the data, integrate the data, and use parallel computing resources. There still needs to be a regridding step for that, and we can help with that through co-location of the data on those parallel resources. One thing that comes to mind is that we were working on grids as a service with the Noggin project a year or two ago. And a focus there was on level 1 and 2 data. And that's one thing that we're really interested in with the STAIR indexing, is being able to work with that ungridded or swath data and making that more usable to the end users and helping folks to integrate very diverse data there. Alternative packaging is also a possibility that is opened up with the STAIR approach, and I'll come into that in a couple slides. For example, one of the things that we did with Noggin is that we developed a kriging package to Krieg level 2 data, for example, and on the right we show a test example of that sort of calculation where we have a level 2 data source with a bunch of gaps in it, and then we took a kriging approach that was slicing and dicing and putting this onto a parallel computer in an automated way, and then coming up with an estimate for what the data was in the gaps. And the idea that I'm trying to get across here is that you'd have to have a step like this to help you out once the STAIR indices actually help you to get the data. One other thing that comes up is that you have the possibility with HDF virtual data sets to set up a system that looks like an HDF file on the front end, but on the back end, it's actually been divided up and distributed across a wide variety of distributed computing resources, either through a parallel file system or through going to a dedicated file servers for different parts of the data file itself. The idea here is that one of the things that you could do with STAIR is that you could actually use the STAIR approach to chunk up the data that is in the HDF file, distribute that data out to those parallel resources so that you can minimize any sort of cross communication. And then when somebody comes along and opens up the HDF file on the front end, it looks like what they've been using before, but when they reach into the back end, they pick up the acceleration from using STAIR to spread the subcomponents of the file across your high performance system. So it's come to my attention that some folks may have some misconceptions about STAIR, and I touched on these a little bit earlier. There's a perceived complexity but I think most of that comes from its unfamiliarity with a new system. What we're trying to do is that we're synthesizing geolocation and computer access. So it's, that's the fundamental part for that co-location. It's not really more complex, and in some ways it's simpler than other recursive tessellations, partially because we give up having equal areas. The encoding complexity, how we actually encode the tree into the index values themselves, our 64-bit words. Now, that's all hidden behind the API, and what we want to do is provide high-level functions like intersections, disjunctions, regions of interest. All that should be presented to the end user via a relatively high-level API. The variety is very important. The data variety is very important. And if you just stick with conventional arrays, which is what everything is built on right now, you lose co-alignment, you lose the ability to scale out to volume in a very in a ready way. So what we believe is that with STAIR, you can scale out in both volume and variety and be able to integrate these different data sets without paying a huge upfront cost and bringing everything together. So in conclusion, this really just calls back into play. The first slide that I put up is that STAIR is a spatiotemporal geolocation. We want to be able to scale to both diverse data, being able to handle variety, and also be able to handle volume as well. We really want to be able to bring levels 1 and 2 data to the public and be able to integrate at that low level in a way that doesn't break the bank. We have adaptive resolution in our index itself, because in some sense our STAIR IDs adapt to the data, and then we use that to help us do our set logic and intersections to help us integrate. We're fundamentally very friendly to scalable and parallel systems, so that translates to the cloud. That also translates into the high performance and high-end computing environment as well. And finally, well, I think it would be extremely useful for us to lay all this out, or write it up in a DGGS format so that folks can see where we're very similar and where we're a little different, and perhaps everybody can understand some of the reasons why and what we actually offer that goes beyond the basics of the DGGS, particularly into scaling to volume and variety. And that is the conclusion.
Cool. Excellent. Well, thank you. And if folks are interested, Quo put a link to a demo animation in the chat. I certainly have a question or two, but I would open it up to anybody on the phone to unmute yourself if you're muted and pitch a question Mike's way. All right. Well, if nobody's jumping in, I will. I'll say I'm fascinated as an engineer. I'm always thinking about separations of concern that allow you to solve hard problems while kind of hiding complexity or not dealing with a part of the problem that you don't necessarily need to worry about. And I really appreciate the separation. So given that, I really appreciate the separation of the kind of analysis or computational mesh use case and the indexing and cataloging and data integration or data co-location use case. And I feel like one of the big complications that comes up there is at some level you end up wanting to use your indexing mesh or your indexing scheme for some kind of computation, even if it's just computing summary statistics on the index.
Right.
I wonder if you can talk a little bit about the potential for, say, summary statistics of level 1 or level 2 data that would get embedded into the STAIR index for the purposes of kind of smart queries for filtered data, data that meets certain criteria. Has that been part of your engineering, or is that something that you're building in?
Well, the first item that we've done some checks on are actually constructing statistics on, for example, the areas of the triangles that we have, because that's a really important figure of merit for those folks who are interested in triangular meshes. And so that's something that we already have built into it. So we do have some of those hooks in there. What we don't have, and what I'm very interested in having, are being able to recursively build the sorts of statistics that you're talking about. And in the literature, there have been some folks who have done precisely that, and so that they can collect statistics about the data sets that they have arranged according to these sorts of recursive indexing schemes, and that they go pretty quickly, and you just traverse your way through the tree and then collect things as you come back up. So that's definitely something that we're interested in. It's just not in there just yet, and is something that is on our wish list at this point.
David, this is Quill, and are you asking whether we thought about collecting like the summary statistics of a data set? Let's say, for example, a temperature and the average of the temperature from a certain data set for a certain period of time. Is that what you're?
Yeah, or I mean, yeah. For me as a hydro guy, like say I wanted to retrieve all data with cumulative precip over 10 inches in one day, right? And I don't care where it is. I just want to go get it.
Yes, I mean we have thought about that. Actually, STAIR is let's say for example, if you work on only because I'm on the I'm kind of related to the hydrology folks, and I'm on the global precipitation measurement mission team. So I'm aware of the things that a hydrologist would like to have. Let's say, for example, you have just one data set, and you want to know a single data set, and you just want to know where the accumulation is above certain things. So that can be done in STAIR very efficiently. And then the other thing is that if you have two different data sets you want to compare, and then they have different resolution, and that becomes more interesting, but STAIR can handle that too. So there's nothing prevent STAIR doing those things. And but the caveat is this. So we assign in the STAIR indices the approximate data element resolution. It's an approximation. It's not exact. Okay, so if you want to talk, say, the accumulation in water volume, then you need to multiply your accumulation in millimeter by the area, don't you? Right? So you will have some error if you do not have the original area encoded into the data. If you just straight using the STAIR approximate resolution, then you will have some error. But if you, in the data itself, you also, like an attribute to the data element resolution, or if its resolution is fixed, then it will be a constant. That will be even better, right? So then you will get, you're just multiplying, doing a dot product. So that's easy too.
Right.
Does that answer your question?
Yeah, it does. Thank you. It's interesting. I mean, there's a lot there. That the distinction between just an indexing scheme and something that you would want to do computations on, especially when you're talking about area and volume.
Right.
It's complicated.
Right. And but this is something that we also considered, because in atmospheric science, a lot of times we are more interested in flux. And when you are interested in flux, then area becomes important.
Right.
right? So what Mike Rilee has just spoken about was the statistic about the grids themselves. Say, for example, the mesh size at a certain level, what is the variation? You know, what is the maximum and what is the minimum, what is the mean of that mesh size? And we do have statistics for that. So it stays, you know, within a factor of 2, maximum divided by minimum area for a particular level. I mean, actually for all level, all hierarchies, it stays within 2. Correct me if I'm wrong, Mike.
Mhm.
And so that is much better, although not the equal area, but much better than the let long we are used to.
Right.
Yeah, usually what I try to do when I'm using the stair spatial IDs to analyze some data is that I pretty rapidly try to get away from the stair library itself, and then I'm just using the index values, because the index values are telling me where the data is. They're actually the location of the data in the array, and then I'm using my my parallel system to collect those to collect those statistics simply by going through a sparse what amounts to a sparse array. And then if I need to get some geometric information, the lat long for a particular triangle or the area of that triangle in order to do a weighted average or something like that, then I can call the library and get the particulars for those particular spatial regions.
I have if no more questions, and I have a pop quiz. Do people understand what we
Does
meant by
does anybody
alternative?
else on the call have a question?
Hi, this is Zhen, and I want to know if you have compared the triangle mesh with the traditional spatial analysis tools about the performance, like the query speed or something like that.
Yes, we did.
Do you have
And
some?
we did. I mean, if you look at our publications and you go on to researchgate.net and search for my name, Kosen, KWO-SEN, KUO, and you will see my publications about stair, actually a little before stair and after stair, and also the demo that I posted, the link that I posted on the chat. Take a look at that. I mean, using stair, we beat everyone hands down. The demo, what the demo is trying to show is that we can do interactive animation. We usually interact with some static image, but not in this case. This case, you are interacting with animation. So that's how, and also on the back end, we have only a cluster of 16 lightweight nodes, and these are not, those heavy fat nodes.
Mm-hmm.
And we can, and the front end, we just piece it together quickly using Google Map, and but the animation is showing basically the integration of 4 different data sets. You can, enlarge the animation, make it a full,
okay.
Full screen.
Okay, yes, that will be very helpful, because I see that if we want to use this indexing mechanism, it needs some investment at the beginning. Yeah. So
yes, indeed.
Yeah, we want to take this approach. We have to make sure that it's better than the tools we're already using.
That's why I asked the question. That's why I asked the pop quiz. You know, I said I have a pop quiz. Do people really understand what our alternative packaging is all about? And Mike, are you still the presenter? Please put up the alternative packaging slide, please.
Okay. All right.
All right, we'll play along with your pop quiz.
Yes. Okay, so I've been on this problem for 7 years now, starting from 2012. And, you know, basically, to scale volume, right? We have a big data intensive problem, right? To scale volume, the only way is parallel processing. How else are you going to do it? How else can you do it? There's no other way but parallel processing. But what does parallel processing mean? That means that, you know, you use many nodes to accomplish one thing with or your analysis with fast speed, right? So each one handles a little piece, and then collectively they go through the whole thing rather quickly. So that's what you know, parallel processing means, right? And then, but the thing is, without simultaneously scale variety, your volume scaling is only partial. It's incomplete. You cannot achieve the kind of performance that we wish, because, you know, in earth science is system science, and that it requires us, you know, in order to gain a comprehensive view, a holistic view, we have to analyze, you know, diverse multiple data sets, right? When we do, say, for example, simple things, you know, I have a new instrument getting me new data, and, you know, it's a follow-on of another instrument, earlier instrument. Now we have to do verification, and we have to verify it with the ground-based observations. So, you know, now already you have to analyze together the past data, the current data, and also the ground-based data, right? So we have to analyze multiple data sets at the same time. But the thing is, the gist of our variety problem is really in the dissociation of our array indices from the geospatial temporal references. So we package our data into these arrays, conventional arrays. You have ij, and then the increments, you know, I increment, j increments, or L increments, M increments, all right? Right, one by one at the time, you know, so the conventional arrays, right? But each ij, L, M, you know, from data set to data set, even from in the same data set, from granule to granules, are pointed at different spatial location, geolocation. So this is what we mean, you know, the swath ij and the grid LM, you know, they are the same indices, they are pointed at a different geolocation. So we have to, because we analyze geospatial temporal data, right? So geospatial temporal are the references of concern, not the INJ, not the LM. But, you know, right now we have to go through the INJ and go through the LM to get to the georeferences. So now the thing is that, okay, so how can we unify this? And that's where STAIR comes in, okay? And the STAIR is a hierarchy. It's a hierarchical. So let's go back to the VDS, yes, the alternative packaging. So imagine that, okay, at the lower end, at some qualification level, Q plus 3, this is where we store actually the IFOVs, right? the data elements, the data values, right? And they are indexed by stair. And we, at a certain qualification level, we know which geolocation will fit into here, which data elements from that granule will fit in here, right? So now imagine that because the HDF VDS allows you to specify, to actually create a virtual HDF file. So now at the we can create a virtual HDF file at the qualification level Q+2. All right, this qualification level, this green triangle, the bigger triangle, actually contains the lower level from the source, 4 from the source, right? And recursive virtual data sets, at the Q+1 level, it can contain 4 of those from the Q+2 level. And at the top one, the darker blue, it can contain 4 at the Q+1 level. All right, now with all this setup, so actually, besides except for the lowest level Q+3, the above ones are all virtual files. It doesn't take up much memory storage at all. So most of the storage is actually at the real, where it's a real file, real granule, right? But now, when you do your analysis, let's say, for example, we go onto the cloud, and you are a very successful getting grants. So you have lots of computing resources, and you can afford to procure in the cloud fat nodes with large RAM memory. Now you can afford to use a greater volume chunk. So then you will read in your data to your nodes at a higher level. But if you are interested only in a small area of the globe, and you do not have big resources to procure fat nodes, and you can only get by with the intermediate nodes, and you have to use smaller data chunks, and then you read the lower level. Okay, and imagine that if all the data sets are packaged this way, right, at these levels, then you could read them in already, because they belong to a branch, right? Each of these belong to a branch of the hierarchy. So that if I'm analyzing, say, NMQ and trim, you just read in the same branch, the same branch for both data sets into the same node. Now you are spatial temporally co-aligned. And then when you do these integrative analysis, you are not generating cross communication between the nodes. That's where you can maximize your performance, and our processing can be scalable in both volume and variety. Does that make sense?
That wasn't a pop quiz.
Yeah.
It makes sense. It's great. I love it. There's some really cool graph properties that you're taking advantage of here that I think people would like to be able to take advantage of in rectilinear quad trees, but is really difficult because you can't make tessellations out of them. It's cool. It's great.
Yeah.
We're at the end of an hour. I really appreciate the talk and the summary. That really kind of drew it all together for me in a good way. So thank you.
You're very welcome.
Yeah, so this has been recorded. I will get it processed and up on YouTube and shared around to the community. This is super cool. Excited to see where this work goes in the next few years. And yeah, I mean, hearing how this ends up kind of relating to and maybe leveraging some of the splashy that is DGGS, and hopefully you guys get some penetration into the NASA data systems world. And yeah, with that, thank you very much, and we'll see you next time.
Thank you.
Thank you very much, David.
Thank you.
See ya.
See you. Bye bye now.
Bye.